Hello, everyone. Welcome. Good morning, good evening, good afternoon. Welcome to today's webinar. I am happy to host today the webinar on pyrazinamide, an API with 4 polymorphs. When are they stable? A webinar presented today and brought to you by Dr. Ivo Rietveld from University Rouen and University Paris Descartes. Before we start, and I introduce to you the presenter today, I would like just to share some information, technical information about the webinar. It is being recorded and it will be made available to all of you tomorrow, I think, within an email. You'll receive an email with a link to the recording and also to a place where you can access the slides presented today by Dr. Ivo Rietveld. If you have any questions, you can make use of the chat function of questions of this platform. We will answer them at the end of the webinar. Or you can write an email at info@crystallizationsystems.com, and in the coming days we will do our best together with our presenter to address all your questions. The webinar will last about 45 minutes, including questions. A bit about Technobis. Technobis Crystallization Systems is a Dutch company located in the north of the Netherlands. We are world-leading technology provider for solid-state research, process development, and formulation. We are on the market since 2005 with more than 600 instruments installed worldwide. Our portfolio consists of 3 products: the Crystal Reader, Crystal 16, and the Crystal 9 instrument. Recently launched last year the Crystal 16 and Crystal 9 version 2 just last November. Some of you might know the Crystal 16 or even the Crystal 9 instrument. If after this webinar you think you would like to test one of our instruments, either contact us directly via the website or send us an email at info@crystallizationsystems.com. Please remember the Crystal 16 is your instrument for solubility, metastable zone with any type of solid-state screening, crystallization, polymorphism, co-crystallization, salt formation, even amorphous solid dispersions. The Crystal line with camera technology that works exactly like a microscope. And also, if you have a Raman spectrometer in your lab, you can easily connect it to the Crystal line instrument. Helps you to develop and optimize your crystallization and or formulation processes. This version, the newer version, the version 2 of the Crystal line, comes with an improved software, image analysis, particle size distribution analysis, and also AI, artificial intelligence based software that helps you in developing your or optimizing your process, mainly giving quite a lot of information on particle properties. Last but not least, the Crystal Breeder, our instrument that works at the smaller scale, at microliter scale, with its vapor diffusion setup and controlled evaporation setup, which are like, it is actually like a gadget type of instrument, which I like to call it, helps the scientists, the chemists to grow single crystals, perform crystallization type of screens. Technobis manufactures this type of instruments, which enables you, the chemist, the scientist in the lab, to measure, characterize, and control some of the parameters, properties related to solid-state crystallization. And I'm sure you will hear much more about crystallization and polymorphisms today from our presenter. I'll go further. And as I promised to you in the very beginning, I would like to introduce our presenter today, Dr. Ivo Rietveld. I finally have the honor to introduce you, Ivo. We were talking about this webinar for quite some time now. Thank you very much for joining us and making this possible today. Ivo has obtained his PhD back in 2000 at the University of Leiden in the Netherlands, and afterwards he carried several postdoctoral research. So he did a few postdocs at University of Delft, at TU Delft, and also in Pennsylvania. Between 2003 and 2007, he worked at the University of Kyoto on the fabrication of thin ferroelectric polymer films by electrospraying. Since 2007, he joined the Faculty of Pharmacy at the University Paris Descartes. Since where currently he's an associate professor, and since 2017 he also joined the University of Rouen. His main research subjects cover thermodynamic stability, resolution of enantiomer mixtures, crystallization, and the stabilization of metastable forms such as amorphous mixtures and metastable polymorphs. Once again, thank you very much for joining us and making this possible today, Ivo. I am now going to make you a presenter, and I think now you should be able to share your screen. The floor is yours.
Let's hope it works. Thank you, Carmen, for the introduction, and thank you for giving me the opportunity to present. I hope that my screen now is visible.
Yes, perfect.
Yes, everything is visible, and then we can start with the presentation. Maybe a slide, there was nothing wrong with the introduction, but it is all the political movements in France and the universities that keep on merging, and since about 1 year, I think, our university is not University Paris Descartes anymore, but merged with others, and now University Paris Cité. But I mean, my working place is still exactly the same. So nothing has changed there. So as we promised, today I will talk about a drug molecule, pyrazinamide. It has 4 polymorphs, and as you will probably see in this presentation, it is a nice model system to look at polymorphism and how you can study, say, the phase behavior of these polymorphs. And that is also why I chose to show this system to you today. Just although I was making this slide and I was thinking, why should I mention this? Because everybody who logs on to this talk will probably know why we care about stability. But just a few sentences about it. We, in particular, when it comes to drug molecules, we would like to avoid polymorphic changes because in general, that means changes in solubility. And next to that, also changes in, therefore, the bioavailability. And that may completely alter the way that the drug works or makes it unusable, etc. But on the other hand, I mean, this presentation obviously will be about polymorphism, about the crystals that we have and that we can use in say, a solid state formulation. But the whole problem also exists the other way around. When you actually have a liquid solution and you want to avoid crystallization also there, you have to be careful about the polymorphs, because if you indeed hit a polymorph that is much lower in solubility, as the famous case of ritonavir, for example, you get a crystallization that you don't intend, and you also lose the efficacy of your drug system. And that said, of course, this is about a drug molecule, so we'll be focused on drugs, but This whole idea of stability also exists in the food industry, where you have emulsions that you want to keep stable or at least persistent. In the pigment industry, where you may not want to have a change in crystallization because it may change the color of pigments. And also, for example, in explosives, where this can cause a problem with the durability of the explosives. So this stability plays in more subject matters, but in this particular case, obviously, we will be focusing on drug molecules, and in particular on pyrazinamide. So this presentation, then, I will introduce pyrazinamide a little bit more before we go into the actual experimental work. I will give a bit of a reason, a background why we actually did this work, or why, in a sense, a PhD student of mine did this work. And after that, we will show you, in a sense, very, very quickly, which experiments we used to figure out what the stability domains were of the different polymorphs that exist for pyrazinamide. And we will conclude with a phase diagram that you can construct. And after that, still talk a little bit about polymorph beta, which, well, the interest in that, why this is worth an extra remark, you will clearly see quite soon in this presentation. So pyrazinamide itself is a rather small molecule. As you can see here, it has a molar mass of 123 grams per mole, so quite small. The temperature of fusion is, on the other hand, relatively high, say 190 degrees Celsius. It's a drug used against tuberculosis. And, well, as you may have figured, there are 4 polymorphs that are named alpha, beta, gamma, and delta, which I have shown here. So these are, say, the main structures, elements that you can find in the structures of these different polymorphs. Alpha is, say, a combination of 4 molecules bound with hydrogen bonding. In beta and also delta, we see the dimers appearing, whereas gamma actually is a little bit stranger in its way it is crystallized, because here the molecules are turned and you see, in fact, chains running through the crystal structure. So alpha is mainly the commercial form that you would find. If you cannot get it by commercial way, or if you would like to have better crystals, generally slow evaporation in water or cooling crystallization in water will provide alpha crystals. Beta is the hard one to get, in fact. There we worked, in fact, with the crystalline, and there we found that cooling at 4.5 Kelvin per minute in chloroform would give you the best quality beta crystals. However, cool a little bit faster and you would find delta in the solution, cool a little bit slower, and there would be more and more gamma appearing. And in any case, it was always very difficult to really get the right cooling rate, so to say, because there would always be some gamma, or going too fast, some delta in the solution. So beta was very hard to get really, really pure. Although sometimes on a lucky day, we had maybe 1 or 2% in there. When it went not so well, it could be more 5 to 10% of a gamma form. Gamma itself can be obtained. It's the high temperature form of the system. You can get it by sublimation at high temperature, or it doesn't matter which form you take. You heat it up in the DSC or you heat it up in the oven, and at a certain temperature, it will always transform into the gamma form. So that can be done. For the rest, you can also get it by spray drying and lyophilization. So obviously, it is the form that crystallizes out rather rapidly if the system is, say, not so very stable, it seems. And then the delta form, kind of, say, a brother or sister, say, of the alpha form, because delta is also stable relatively close to room temperature, and you can therefore get it by cooling crystallization, either in methanol or 1.4 dioxane and some other solvents too, but relatively easy to obtain. Well, so the stable, and here I talk about stable in the sense that crystals can be stable, or from a thermodynamic point of view, which for me is the real stable. But within a drug molecule or other applications too, you can also kind of engineer crystals to be persistent. That means, so dynamically, they simply don't convert very quickly into a more stable form. And so that stable can be interpreted in different ways. In the literature, this is often a bit used either one way or the other, without not always being very clear whether the stability is dynamic or really thermodynamic. So what is known about the system? I will also show some energy temperature diagrams just later on, but alpha was, when we started this research, and maybe still is, considered to be the stable form at room temperature, the commercial form also. Delta is also stable either roughly at room temperature and just below. So the delta form, which you can see here, alpha, if you crystallize it very quickly, you will get this type of crystals. From sublimation, you can get much nicer crystals, but you should do this sublimation at relatively low temperatures, otherwise, obviously, you will obtain gamma. So this is a bit of hard work. And after that, the beta, you can get it from slow evaporation from methanol, but always with other forms around, either delta, alpha. And this is a photo actually obtained by the crystalline, where we have been doing lots of experiments to get beta in the most pure form possible, where we kind of fine-tuned the cooling crystallization of the beta to do all the rest of the measurements that you will see later. Because to do all these DSC measurements, etc., you would want to have the purest crystals possible, so that you get the best data possible. Right, and after that, we also got the gamma crystals mainly through sublimation, or if you just needed the powder, then heating up is the easy way out for this particular system. The question that was, in a sense, still asked, and for that, I show two energy temperature diagrams here that were known in the time that we started with this research, which was in about 2017. Two papers that I suppose slightly by accident got published roughly around the same time. A few things that are interesting here are, as you can see, the transition that was listed for the alpha to gamma transition is about 155 degrees Celsius. Then you can see that alpha is stable up to or down to room temperature, and after that, delta is supposed to be the stable form all the way down to 0 Kelvin, is the idea. Here you can see the beta form, which is kind of slightly below gamma, and you can see this in this phase diagram also, where the beta form is kind of floating high in among the forms, and definitely not considered to be a stable form, more delta than alpha again. And so what they clearly agree about is gamma is the high temperature form, alpha intermediate, and delta then the low temperature form. Well, that idea, in a sense, I'm not going to change, but we are going to add a few details to these phase diagrams. Just to explain why bother if you, in a sense, already have this information. Well, we came across the fact that the gamma form is the high temperature form. And if you make gamma crystals, which is metastable at room temperature, therefore could give, say, a higher solubility if you would like so for pharmaceutical applications. And normally, if you make gamma crystals, they convert into alpha crystal relatively quickly. Over a few days, generally, everything would have turned into alpha crystal. But what we found in our lab was that if gamma would be spray dried with certain additional compounds like dimethylurea, for example, these gamma crystals would stay and remain for years intact and not convert into anything. So the question is then, what is going on here? And that, of course, was one of the axes of the research. But one thing that you also would like to know is how stable is everything actually? I mean, we see gamma transforming into alpha if it's not of high quality. So alpha should be the more stable form, but where actually is this gamma form stable and where starts the stability domain of alpha? So that was one of the first questions that we asked, and that is why we prepared this phase diagram. Well, what we obviously first started with, because you need all these crystals that I in fact already showed, so we listed, we did say tests in different solvents. I would say nowadays we would use the crystal 16 for this because that is what we have nowadays. But at that point in time, we still used students. We still use students. Being at the university, that is an easy way out, so to say. But that allowed us, therefore, to see which different solvents we could use for crystallization experiments. And after that, obviously, we got to our solutions of which solution to use for which particular form that we would obtain, and then use cooling crystallization or slow crystallization, etc., at ambient temperatures to obtain our crystals. Well, after that, we went into our experimental part to figure out what is really the hierarchy of the different forms, strangely enough. So I'm not sure.
No worries.
Anyway, so we are the experimental approaches here where we did a lot of DSC measurements. I just will show a few of them. Obviously, this is the behavior of the delta form. And what you can see as a function of the heating rate is that if you go relatively fast, delta will immediately convert into gamma. Going slightly slower, this delta form will have formation of alpha and gamma. This we also checked with X-ray diffraction, which I didn't show here. And you can see here a little bump, I hope. That is the entire conversion of alpha into gamma, and going even more slowly, delta will turn into alpha, will turn into gamma. And that is shown in the graph on the side. Here you have the heating rate, so going up in heating rate. You have the temperature here. What you can see is therefore at the very low heating rates, you have an increase of the, at the very low heating rates, you see this double peak over here and over here. If you go slightly faster, then this is the purple point that it coincides with this one, you see it lower. And even higher heating rates, you have the immediate conversion of delta into gamma. I also plotted, but these are different measurements. This is alpha turning into gamma, where you can see that in particular delta behaves itself differently because it turns immediately to gamma over here. Whereas if you go very slowly, then you see that the system actually falls back to this alpha gamma system. What you also see is that as a function of the temperature, these transitions are going lower and lower, and it's actually very difficult to put a finger on where the actual transition temperature or the equilibrium temperature is, what as a thermodynamic well, if you are interested in thermodynamics, would like to know where this equilibrium temperature is impossible to decide by DSC. However, we can have an idea of the enthalpy of transition through the different peaks. Same story for the beta to heating beta, where you can have one peak, which, and there I show with X-ray diffraction, you get actually a mixture of delta and alpha that arrives. And this mixture of delta and alpha at a certain point will also transform into gamma. You can see that here very well. And after that, you always have the melting peak of the gamma form. So from that, you can see that gamma at a certain point will always form. Throw this again, absolutely impossible to put a finger on the transition temperature, the equilibrium temperatures, but you will have an idea of how much enthalpy is involved with the different transitions by studying this very carefully and with different quantities. So that is for the different crystals. Now, a bit more precisely looking into the alpha to gamma transition, I showed already some results of this. Here is the peak of the alpha to gamma transition. It was also studied in these two other papers that I showed to you quite extensively, and they already saw that as a function of the heating rate, this went down. But as you can see, it is just impossible to put a finger on this actual transition temperature. And it just keeps on going down, and at a certain point, the DSC just cannot go any slower because you don't see any peaks anymore. So what we did was we put different samples into an oven at given temperatures. And obviously, here we go off alpha, but we also had gamma samples at these temperatures. But this is just to show the final result that all alphas above a certain temperature turned into gamma. Then we, at a certain point, saw a mixture appearing where just a little bit of gamma was formed. And at the opposite side, so to say, where the gammas were put into the sample, we could see alpha form at a given point. And by like cross-referencing this to a series of experiments, we could put the finger on the equilibrium temperature of 392 Kelvin or 119 degrees Celsius. But that was quite a bit of work. Now, this DSC measurement, therefore, gave us the possibility to have, on the one hand, enthalpy differences, and the oven gave us at least an idea about the temperature, equilibrium temperature between alpha and gamma. But the rest was much more difficult. So here, and this I think is rarely done because it's just a lot of work, but we used vapor pressure measurements. And I would say, in a sense, we're lucky with the pyrazinamide because it is so reluctant to transform, and it takes a long time in the DSC. You have to heat up at very high temperatures before you have actually the transformation of one form into the other. Therefore, it is relatively easy to use vapor pressure because the system stays intact. And that allowed us to do the vapor pressure measurements for all four forms. Here you can see the beta form, there the delta form. Then we have the gray gamma form. And
Ivo?
Yes, one thing is, so we have the vapor pressure here. This is done with a Knudsen cell. I will not go into the details of how that is exactly measured. What is more interesting to know is, first of all, the vapor pressure. So the vapor pressure allows you to determine the Gibbs free energy basically directly, because the vapor pressure is a direct reflection of the vapor pressure. And the graph there at the top, you have to pay attention. It is a function of the temperature, but it's the inverse temperature. So on the right side, we have room temperature, 294 K, which is about 20 degrees. And on the left side, we have 345 K, which is about 70 degrees Celsius. So what we see at 70 degrees Celsius, that the beta form is the has the highest vapor pressure, so it's the least stable. But we also see that alpha form is the lowest vapor pressure, is the most stable. So what we can see here, for example, is that the gamma form, we see it especially on the right side, and then it comes crossing through all the other forms and goes towards the alpha form on its way to cross both forms the moment that they hit 119. In principle, with these curves, we determine the temperature of 125. If you can see how this runs almost parallel, you can imagine that a little bit of an error in any measurements may shift these lines very quickly, and therefore the temperature, the transition temperatures may be actually shifting also rather rapidly. So a very precise measure of the transition temperatures I cannot guarantee with this, but at least it gives you an idea, and it also gives you the order in which the different forms will be stable or less stable, because where they cross, obviously that changes much less quickly, because that depends on the different slopes of the different forms. Or in which order they cross, I should say that. So important here to see is that alpha is stable at room temperature, but you can also see if you go down to room temperature, you see the delta form, which is not remarked, but it's the yellow line crossing the alpha form. So you can see that really at room temperature, alpha and delta are basically have the same stability, thermodynamically speaking. And you can also see that the beta form comes in falling down rather steeply and must be crossing all those other forms at low temperature. So beta form must be stable at low temperature. So these things you can see from these vapor pressure measurements. Yes, could you switch to the next slide, please? Well, after that, obviously, this may not be of interest to anybody who is just interested in what is the stability behavior and how does my phase diagram roughly look like. But while we are academics, we like to go a bit deeper, a little bit further. So we also measured like the specific volume of all the different forms, and as a function of the temperature and as a function of the pressure. Here, this is just an example of the delta form, for example, to show the expansion and decompression, or in this case, the compression under pressure of the delta form. If you can switch next slide. And these then are the results of all these measurements. On the left side is measurements that are done as a function of the temperature. On the right side, measurements that were done with the synchrotron under pressure in the Soleil beamline in just south of Paris. But the interesting part that you can see here, if you look at the blue points and the black points, the blue is the delta form, and the delta form actually is kind of were the dimers, but these dimers are kind of lined up and they form layers that are relatively easily compressed. And you can really see that if you go down in temperature, they very quickly shrink and come very close to the specific volume of the gamma form. Looking on the other side, you even see that under pressure, this delta form has even a lower specific volume than the gamma form. So it actually crossed this line. I mean, some people may say, who cares? For people working in thermodynamics, this is nonetheless something that is rarely seen and has other, how you call it, effects within the phase diagram that I will not go into. But nonetheless, this is of interest from an academic point of view and maybe even further. If you could go to the next slide, please. So here I'm basically ready to wrap up, and sorry for the delays that we had with the other the presentation that doesn't want to show itself. But with all this data, so in particular the DSC data, and in particular in this particular case the vapor pressure data, we have temperatures, we have enthalpies, and therefore we can make a phase diagram, as I have shown here, as a function of the temperature with the different transition temperatures. So the green line we could determine, for example, by DSC. Then we had the blue line, the alpha gamma transition, which we obtained by oven. And all the other measurements, they will be less clear, less well-defined, so to say, because they are all from the vapor pressure measurements, and there the error obviously is much larger. So this allows you, say, to position the different transitions, possible transitions between the different phases. Beta to delta is the yellow one, for example, within the phase diagram. If you could show the next slide. And after that, you can even relatively easy, even without measuring anything under pressure, put a pressure element in 2. And that you do by the Clapeyron equation, which is shown up there, where you get the slope, dp dt, of a certain equilibrium within a pressure temperature phase diagram. And that just depends on the enthalpy of transition, so the enthalpies that we obtained out of our DC measurements, and obviously the temperature, the equilibrium temperatures, but also the delta V, that is the change in the specific volume on a transition. And that we basically have been able to determine as with an X-ray equipment as a function of the temperature. Those were the curves that I showed on the left in one of the previous slides. So this also is in principle possible in any laboratory that is relatively well equipped with X-ray equipment and a DC equipment. If we can go to the next slide. So then you end up basically with a phase diagram that can look like this, where you extrapolate after that the slopes that you get out of the Clapeyron equation. Obviously, you will not find any new phases, because for that you will really need to have to look at high pressure and see what the system does. But pyrazinamide doesn't move that much, so there is little to see in the sense of phase transitions. In addition, we also did measurements that, again, we can do with colleagues in Barcelona, where we used high pressure thermal analysis. And on the right side, you have a little graph where we actually measured the alpha gamma transition and also the gamma, the fusion of gamma, so to say. Watch out, because in this scheme, there's also alpha liquid, but that is a calculation that was put in this little graph on the side. So we measured the gamma liquid transition and the alpha gamma transition and could place it in this phase diagram. Also, again, specific for us, but it helps us to understand the overall point of view of the phase behavior of the system. If you can go to the next slide. This is just to show you how it works. I mean, this is a high pressure differential thermal analysis. It's like a DSC, but a bit more simple. You measure temperature differences of a sample and a reference. Here, the reference is the T, but that doesn't matter. And you put it basically under pressure with a liquid. And that you can control depending on the temperature. You can calculate pressure and measure the temperature also, and in that way you can work out, say, the phase behavior under pressure. This system can go up to about 300 megapascal. There is another system in Barcelona that can also go up to 500 megapascal. The trouble is, combining heating and pressure is often a little bit a tricky thing. We can go to the next slide. And there, with that, basically we get at the end of the presentation, this is basically the conclusion. So on the left hand, you have a pressure temperature phase diagram of all these 4 phases of pyrazinamide, in which we have clearly in the center alpha as a stable form at room temperature and under, say, 0 pressure. 1 bar is not very much. If you can see, we go up to 150, 200, 250 megapascal. So 1 bar, that is 0.1 megapascal. So we're really at the lowest line there where we live, so to say. So alpha is the stable form at room temperature. But you can see also that delta and alpha are very close together. Somewhere around room temperature, they transform into each other. So basically both forms could be considered stable at room temperature. But we see also that beta has appeared as the low temperature form. And gamma obviously is also around. For those people that prefer energy temperature phase diagrams that you can find in the top corner with all the temperatures that are listed that mainly have been obtained from the vapor pressure measurements, with some obviously the alpha gamma that came out of the oven experience, and the melting point from the DSC measurement. So both ways to basically have an idea about the stability, and there again you can therefore see that the beta form, instead of being somewhere floating between alpha and gamma, clearly also cuts through and has a stable form at low temperatures. And then we can go to the next slides. So seeing this, and also all the frustrations that we had with getting a nice beta crystal, we did one final experiment, and that was simply recrystallization of pyrazinamide at low temperature, at -20, in this case in dichloromethane. And we had indeed almost pure beta. There was a little bit of delta in there. It was really a tiny little bit, and we don't know if that is just due to the fact that we did our measurements at room temperature, so we had to bring up the temperature of our pure beta, or that maybe we should have done the crystallization still at a bit of a lower temperature. But basically, the sample was pure beta. So that showed that it was much easier to obtain beta at these very low temperatures. So much for all this work that we did in advance, but how else can you know about all that? And we can go to next pressure. Yes, I forgot to say that also some calculations, but maybe you can also look it up by Hoser in Acta Christ, had also calculated already that beta was stable at low temperature. So that, in a sense, confirms our findings too. So if you can go to the next one. With that, we basically get to this conclusion, which is the pressure temperature phase diagram, or for those people that like it or prefer the energy temperature phase diagram on 2 pages before. And as an academic, I prefer to conclude we think now that we know the phase behavior of pyrazinamide, because you never know what comes in between, and that there is still a problem with one or another measurement that needs to be done more precisely, but this is most likely how pyrazinamide is supposed to behave. Next slide. Then, obviously, I do need to thank a few people, in particular Kang-Lee Lee, who was the PhD student who did most of this work and very, very much of all these DSC measurements, all these other measurements that needed to be analyzed, etc. So the largest part of the work was done by her. I should also mention Marine Verger-Després, who did actually the vapor pressure measurements in Sanofi together with Benoît Robert. And after that, we have Josep Luis Tamarit and Maria Barrio, who did the high pressure measurements together with Kang-Lee, who was also in Barcelona at that time, and some other people that were involved either with synchrotron measurements or with the PhD thesis of Kang-Lee, Gabin, Jean-Paul Itier, and René Séolin. Then the next slide, just to thank everybody for your presence at this webinar, and my apologies in a sense for the fact that somehow we had to change this presentation from one form to another. If you have any questions either about this pyrazinamide system, you can of course read the Christ&Com paper that is in principle open access, so you can in principle access it freely. You can send me emails, either uparis.fr or unef.rouen.fr. And if you are really interested, there is another possibility, maybe also for Carmen to come to Rouen. But we are planning to organize a conference on phase equilibria, so really involving this kind of systems, but much more nonetheless, in October in 2023, so this year.
Okay, looking forward to it, Ivo. Thank you very much. Thank you for sharing this. I think if I call it case study, it's too less. It's for the amount of work and also some challenges and struggles on the way that brought this pyrazinamide system. Really impressive, the amount of work. While you were presenting, we have a few questions I will read now to you. But while you were presenting, and triggered by your comment in the beginning about the crystalline instrument that you have used, I recall quite some time back you had a crystalline modified crystalline, I think, in your lab or in Rouen, connected to a laser or so. Is it that
yes,
you have used for this one, or is another compound?
No. That was yeah. We tried to use it with a laser, but in fact, at that point in time, I think the laser was slightly on the powerful side, so it was difficult to use. No, we used in fact simply the camera that came with crystalline for these experiments.
Okay, and the camera is just to detect the different shapes and forms of the
different crystal shapes. Yeah, I mean, there's also the possibility to do it with Raman, but we didn't have a Raman equipment at that point in time. So yeah, we did it, and basically we saw the crystallization, and since we knew roughly which temperatures or which sequences, so to say, gave particular crystals, Kang Lee in that case just did measurements, and after that did X-ray determination to see what the mixtures were that she obtained. But the camera was used to see the crystallization event happening, and it allowed her already quite quickly actually to distinguish between different forms.
Yeah, indeed, that was also, it's one of my favorite things of the crystalline instrument, that the cameras and the ease of use and how you easily can detect something, and then, you go to the next step in a very simple way, let's say, helps quite a lot. But maybe I'm a bit more not so objective and more subjective, because I like these instruments quite a lot. I have a few questions I will ask you. Somebody has a question related to, is there an enantiotropic relation between gamma and delta?
They're all enantiotropic, in fact, because you have if you can go back to the energy temperature diagram, which is one more. Yes, this one. Oh, this one. No, too much.
Oh.
But that, I would say, is maybe easier to look at the original slides once they can download it, say, from the website. But here, in principle, you have everything. And since you have beta being stable against delta, being stable against alpha, being stable against gamma, you basically have a hierarchical stepwise decrease in the stability of the system. That means, therefore, that also delta and gamma have an enantiotropic relationship, and both can turn to the other. And if you look at this diagram, beta gamma, I think, is found at 314, if I'm not mistaken. So that would be their crossing point and the equilibrium temperature, roughly speaking, coming from vapor pressure. So yes, they all have with each other.
Another comment from another attendee. Beta form seems very difficult to obtain as a pure form. How did you isolate the pure form in order to conduct the vapor pressure experiments using the Knudsen cell?
Yes, I expected that question. Actually, that was hard work by Kang Lee. In part, it was a matter of crystallization. In part, it's accepting that you have a few percentage of the other forms in there, which can always cause a problem for your measurements. I think We also isolated a number of single crystals so that you know for sure you have this beta form and measured those separately. And then seeing the steepness of the line, considering that all the other forms at a certain point are less stable, you could expect even that this beta form has an even more steep behavior if it would be alone. So that would only make the conclusion stronger that beta actually has a stable form at room temperature. Sorry, below room temperature somewhere.
Yeah.
The point is just that the actual transition temperature between delta and beta, I don't dare to say that it is either -50, -20, or 0. There, I wouldn't dare to say because it's just too difficult.
Yeah. The last question, because it's already a bit late, and could it be possible that beta form converted during isolation? Was isolation at room temperature, or was there any PAT used during this stage to monitor any phase transitions?
Well, all the phase transitions we have monitored in the DSC on a constant basis, and actually at room temperature, if you would have a pyrazinamide form either beta or delta or alpha, it would barely not convert. As I said, gamma does, because it is really a high temperature form, but in certain cases it also did it so in fact, by DSC, all the measurements that we did under room temperature conditions and slightly above, slightly below, there was no conversion. And within the vapor pressure measurements, we kept within the transition points that we saw within the DSC. So in principle, everything should have worked out fine. But there is always a risk that something converts in the meantime.
Indeed, indeed. I do see another question now from Nicolas Ramos. Okay, maybe the last one. And he says something like this. Maybe the question is too far to be answered in a general sense, but what does avoid the less stable forms, less stable within brackets, to transform into the stable one? So what does the less stable one need to do to convert into more stable?
What it needs to do to convert in a more stable one. Well, for the pyrazinamide, this is still in a sense a difficult thing to answer, but one of the issues is probably stacking faults in the crystal structure that are probably very, very important. Pyrazinamide overall seems extremely reluctant to change form, to change polymorph. So the more a crystal is not perfect, the more there are points within the crystal where things can start moving. And I think that is one of the most important elements for pyrazinamide. After that, any system, any crystal system molecule will have its own particularities for sure. But I think stacking faults is really one of the key issues.
Thank you very much, Ivo. I will stop here. If anybody has any other question afterwards or thinking about this topic and a question pops up, they can always write either directly to you, Ivo. Here is the email address of Ivo emails, actually, and or you can also contact us at via the website or at info@crystallizationssystems.com. Spoiler alert, our next webinar will be on the 23rd of February, brought well, I will not say who is going to present it, but I would say that next is are co-crystals on the list, let's say. So if you're interested in more solid state research and co-crystallization, still a lot of phase diagrams. On the 23rd of February, you will hear a bit more about it. Once again, Ivo, thank you very much for making this possible, for sharing with us this interesting case study, and hope to see you soon, maybe in October in Rouen.
Maybe Rouen.
Yes. All have a nice day or a nice evening. Goodbye.
Goodbye.